Okay, so hello everyone. Thank you for joining the Atto Fridays today. We're going to have the last session of our season of 2022. And this is going to be a hot topic session with early career researchers. And it's a pleasure to have the three of them here. We're going to hear from Xin-Yao Liu, Simon Brennecke, and Antonia Freibert. It's going to be focused mainly on machine learning, but we are also going to have a nice X-ray session. So thank you all for joining and supporting the early career researchers in our field. We are looking forward to the talks. And the first one who is going to speak is Simon Brennecke. He is a PhD student in the group of Manfred Lein in Hanover, Germany. And he's going to talk about two publications in which he looks at photoelectron holography, and he's going to do the quantitative modeling of interference in this situation, and he's going to argue about the subtleties that one needs to take into consideration. And also, he's going to show how you can deal with inversion problem, mapping from final to initial conditions. Actually, it's interesting because we started inverting and now we're trying something forward, and they started forward and now they are inverting. But this is not a trivial matter, and we're looking forward to hear about how one can use clustering to solve the inversion problem and to make it versatile. Okay, so if you're ready to go, we are. Feel free to start. Afterwards, we're going to hear from Antonia Freibert and Xin-Yao Liu. Looking forward to the talks as well.
Can you see the screen well?
Everything is fine, yes.
Then thank you for the kind introduction and for the invitation. So I'd like to talk about the Coulomb lens and strong field ionization. And I think probably most of us, when they think about a lens, they think about classical optics of light waves. For example, a Gaussian light beam that is focused by a lens to a point, which means a 2D manifold of optical rays is focused to a point. And then, of course, when we look at the intensity across the focus, the intensity changes and peaks at the focus. And we all know that at the same time, also the phase of the beam changes, and this phase change is known as Guy's phase anomaly. And if you now zoom out and look from far away, much larger than the Rayleigh length, then this phase change looks like a phase jump of pi. And of course, we do not only know light waves, but also matter waves or acoustic waves. And hence, we would expect that in these types of waves, there are similar phenomena. And in this talk, I want to talk about electron waves produced by strong field ionization. So we first consider strong field ionization in linearly polarized fields, which means we have atoms in short, strong, typically femtosecond laser pulses with wavelength around 800 nanometers or even longer, and field strengths which are high enough that the electric field strength of the laser field is in the same order of magnitude as the electric field that binds the electron to the core. And in this special strong field situation, we know that the ionization process can be described by the famous two-step model, which means that electrons are first liberated by either tunneling or multiphoton processes. They appear then in the continuum at certain initial times with initial velocities. And then, they can be often well described by classical particles, which are driven by the laser's electric field, but typically also influenced by the ionic Coulomb field. And an example of a trajectory is, for example, shown here. So the electron appears at the tunnel exit. For this special time of release, it is first driven out by the electric field, then the electric field switches its sign, so it's driven backward, it scatters, so it's strongly influenced by the ionic core, and hence it is deflected. Of course, such a single trajectory is not is not it is not unique. There are many trajectories. For example, you cannot only consider this initial velocity, but you can rotate the initial velocity around the polarization axis here in linearly polarized fields. And then you get the surface here of trajectories, which means that along each angle you have one trajectory, so you have a 1D manifold of trajectories. And importantly, all these trajectories are focused here when they pass the polarization axis in the same point. So we have also some focusing, some Coulomb focusing of the electron trajectories here in this strong field ionization process. And hence somehow this Coulomb field acts like a lens. And in agreement or similar to optics, we of course expect an enhancement in the ionization probability, which was already predicted in the 90s. There were also enhancements seen in the photoelectron momentum distribution. But what we also expect is that when such an electron wave passes here a focal point, that it phase jumps or it phase changes. And this is this well-known Guis phase anomaly. Importantly, such focusing in this sense here only appears in 3D, because here we need this 1D manifold of trajectories. If you consider the 2D situation, we only have two trajectories which cross, and this is not the focal point. So we expect different phases after focusing between a 2D situation, or this typically often in theory considered 2D situation compared to the real 3D situation. Of course, we cannot directly measure a phase of an outgoing electron wave packet, but we can interfere two electron wave packets and consider the interference pattern. And a quite famous one is here the photoelectron holography, more precisely the spider type interference, which was already discovered by Huysmans 2011. And here we have these interference fringes, which are roughly parallel to the polarization axis. And they are actually caused by the interference of a reference wave packet of direct electrons, here shown as a blue trajectory. And this blue trajectory is only weakly influenced by the core. It does not pass a focal point. And it interferes with a signal wave packet of rescheduled electrons. And these are exactly this focused electrons which are introduced before. And hence, of course, in the interference pattern, their phase difference determines the exact fringe positions. So let us look on this situation from a theory perspective. To this end, we solve numerically the time-dependent Schrödinger equation for helium 800 nanometer. And for simplicity, we use a short 2-cycle laser pulse. However, the things I will present in the following are also correct for longer laser pulses, but then, of course, ATI rings and so on make the analysis more complicated. And then we did one calculation in 2D and a second calculation in 3D, where we consider here a slice through the 3D photoelectron momentum distribution. And I think two things are quite prominent. The emission strength in 2D and 3D is different. And in addition, if you look here at the interference fringes, for example, this holographic pattern roughly parallel to the x-axis, then you see that in 2D, the central fringe is much smaller than in 3D. So the fringe positions are different in 2D than in 3D. And this is already a qualitative sign of this Coulomb focusing and the associated GUI phase in 3D. However, we want to model it quantitatively, and I think in strong field physics there is already a zoo of models. In particular, successful to model holography are models based on this path integral, so these models in this region here in this schematic illustration, and hence also our model follows roughly the ideas of these previous models. However, what is missing in the models? To look at it, what we do is we use a semi-classical approximation to Feynman's path integral and follow the idea of the two-step model. So in the first release step, which we treat with strong field approximation, the electron is at rest, and there the initial conditions for the later motion are defined. So we have some release times t0, some initial velocities, and some tunnel exit position, and we can parameterize them in the spirit of SFA by means of an auxiliary momentum p prime. Afterwards, we treat the motion classically. So we propagate classical trajectories which are governed by the laser's electric field as well as the Coulomb attraction. And then the photoelectron momentum distribution can be calculated here as this sum over the different trajectories. And I would say two terms are quite familiar. One is this action term, where the action is actually collected along the classical trajectory. And the second one here is an ionization matrix element. And the modulus squared of this ionization matrix element is somehow the ionization probability. But then we have this middle term here. And this middle term I called here a prefactor, and it has two important ingredients. One is the Jacobian, or more precisely, the modulus of the Jacobian, and this determines the weighting of the trajectories or influences this weighting. And then the second one, even more important for our observations, is the Maslov index nu, and this represents phase jump as focal points. I will consider these two ingredients in the following more precisely. So when we look here at the sum, we have to sum over all trajectories with a given final momentum p, which means we have to determine all initial conditions, here represented by this p prime, that are mapped by the classical dynamics to the given final momentum p. However, this is typically a quite cumbersome task, because what we can do easily is to solve the initial value problem, which means we give some initial conditions here, propagate our classical trajectories, and get a final momentum. This is done easily. But what we need to do is, we want to look at one final momentum, and we need to find all initial conditions that are mapped to this final momentum. And in general, we do not even know how many initial conditions that are, and we do not know at all where the initial conditions are placed here in this plane. So we thought about it, and we came up with one possible solution. So one solution would be, of course, simply use Newton methods or something like that to solve this inversion problem. But this has some difficulties. So we invented a different method. And to this end, what we do is we sample initial conditions, shown here. Then we calculate the trajectories. We get some final momenta, shown here. And we do it with many points. So we somehow scan this function d, which map the initial conditions to the final momenta. And we do it again and again and get many, many points. And then we want to consider one final momentum in the space of final momenta and look at a small bin around it. And if you only consider those trajectories which end up in the small bin and consider their initial momenta p prime, then you see that here some small agglomerations are formed. For example, here four small agglomerations. And it is important that these are not 4 points, but these are 4 agglomerations of many, many, many points, as you can see here in the magnification. And now the important thing is you have to identify those different agglomerations. And now here the machine learnings come into play. So what we use is a clustering algorithm. This can be classified as unsupervised machine learning. And this clustering algorithm takes this initial points p prime here, all these points. And what it does, it identifies the clusters. For example, here afterwards, after the clustering algorithm has identified the clusters, I can color mark them, for example, here in red, blue, green, and orange. And we in particular use such a density-based spatial clustering with applications of noise algorithm, which is, for example, implemented already in Python and works quite well. So what do these clusters physically mean? These clusters physically correspond to different types of trajectories. For example, all these points here in the blue cluster have nearly the same shape, and it is a direct trajectory. So the red cluster is associated with such a rescattering trajectory we discussed before. So when we have identified the different clusters, we have identified the different trajectories which interfere with each other and form the photoelectron momentum distribution. So we can use out of each cluster one representative trajectory, and then we have solved the inversion problem. So now we know which trajectories interfere with each other, but in order to calculate our photoelectron momentum, we know which trajectories interfere, and we cannot only do it for linearly polarized field, but this clustering method is relatively versatile because you don't need to add in some physical intuition. You simply first shoot your trajectories, then you apply the clustering method, and then you get out the clusters, and hence you have a solution of the inversion problem. And here, for example, we used a bicircular field, and also here we can identify the clusters. Here we have more clusters, 10, and it works quite well. So now we have identified our initial conditions and the trajectories, but what we need to calculate actually the photoelectron momentum distribution is the Jacobian and the Maslov index. And probably we are all aware of having a trajectory and associating a semi-classical phase to the trajectory. And for the Jacobian and the Maslov index, we can now associate a small volume element in momentum space to the trajectory. So we have here a trajectory in momentum space shown in red because we want to evaluate in the end photoelectron momentum distribution. We choose here a description momentum space, and we associate a small volume element to the trajectory, and then we look how this volume element evolves in time under the classical evolution. And you see that, for example, for this trajectory, it changes. And this change of the volume element in the end, well, the associated oriented volume is then this Jacobian J here. And now you see here for the blue situation, you have a very special point because there the volume vanishes. So J is 0. And this vanishing volume indicates a focal point here in momentum space. And for such a focal point, you find a direction in the space of initial conditions or a zero mode, such that when changing the initial conditions in this direction, in this example, for example, along the x-axis, your momentum at this focal point, capital T, does not change. So it's here the same. And hence, because of this, it's called a focal point. But now the important thing is that the Maslov index can only change at this focal point. There it jumps. And hence this Maslov index exactly represents this Guis phase anomaly, which we know from optics. And to calculate the jumps of the focal points, you can, for example, consider this paper here. So this was quite abstract. So we can, for example, consider the special case of linearly polarized field. In linearly polarized fields, we know that we have this nice rotational symmetry around the polarization axis. So here the x-axis. So if we want to calculate the photoelectron momentum distribution in one slice through the PMD, we only need to consider classical trajectories in this plane. For example, here the XZ plane. Which means in 2D and in 3D, whether we consider the 2D or the full 3D dynamics, we have the same trajectories. However, the associated Jacobian and Maslov indices are different in the 2D and in the 3D situation. And this exactly resembles this modulation of the amplitude due to Coulomb focusing and the modulation of the phase due to Coulomb focusing. For example, here for the Maslov index, in addition to the 2D Maslov index, in 3D, we have to count the number of zero crossings of this lateral momentum component along the trajectory. And this means that in general, a slice through the PMD in 3D, not even for linearly polarized light, is equal to the PMD in 2D. And hence, because our model does include this important properties of the prefactor, our model can reproduce this difference between the 2D and the 3D TDSE, which we saw before. So we see here a different emission strength in 2D compared to 3D. And what we also see is when we look here at the fringes, that the fringes look different. And we will do it here now in detail. So as said before, the holographic pattern is formed out of a reference wave packet and a signal wave packet. And also here our momentum space analysis showed that this direct reference wave packet has Maslov index 0. However, the scattered wave packet, there the calculation indeed showed that in 3D it has Maslov index 1. In 2D, because there's Coulomb focusing absent, it has still Maslov index 0. And this momentum space description in the classical model is indeed in agreement with the simple position space intuitive interpretation I gave in the beginning. Hence, if we look here at slices through the PMD, in 2D, one can nicely describe the TDSE when when neglecting Maslov space in the semi-classical calculations. However, in 3D, here the fringe positions are systematically off, and only including Maslov's index, or only when Maslov's index and hence Gui's phase anomaly is included, one can correctly predict the interference fringe positions. So till now, we only considered linearly polarized fields. And hence probably Coulomb focusing looks like something quite special, but it is not. So Coulomb focusing is a quite general property in strong field physics. As long as one has a strong interplay between the ionic core and the driving electromagnetic field. And to illustrate that, we can consider here the example of a bicircular counter-rotating field with a relative intensity ratio of 3, such that the field looks like this here in this schematic illustration. And for such types of field, rescattering is quite important. And it has already pointed out theoretically and shown experimentally that in these types of field also interferences appear in the photoelectron momentum distribution. And here I show again a PMD from numerical solution of the TDSE in 2D and in 3D. And you can again see that there are differences in the 2D compared to the 3D PMD. For example, if you consider here the interference fringes, they look here relatively different in the 3D situation compared to the 2D situation. If we now use our model, we can indeed reproduce this difference quite nicely. And this is because, again, here in 3D, we have Coulomb focusing, and in 2D, we don't have Coulomb focusing. To look at this in a little more detail, we can consider here this interference fringes, which are roughly parallel to the negative px axis. So we look at these fringes here. And the analysis then showed that these fringes are caused by interference of a direct non-scattered trajectory, which is shown here in blue. And the actual analysis then also revealed that the associated Maslov index is 0. But we have also here a scattered trajectory with, in 3D, a Maslov index of +1. And again, the scattered trajectory passes a focal point. And to see that, we can here again use this position space description. And instead of choosing the initial conditions for the red trajectory, which is in the polarization plane, we can start other trajectories with a slight initial velocity in z direction. And then first these trajectories here diverge, but then they are focused to one point, they pass this focal point, and afterwards they diverge again. But after passing the focal point, they again have collected a Gui phase. Importantly, for this more complex, non-trivial situation, we don't have a simple formula for the 3D and Jacobian and 3D Maslov index, but here we really have to evaluate the complicated formulas. But when we then consider the interference pattern for these two trajectories, it is shown here, and we have indicated here the lines of minima, either when we include Maslov, the difference in the Maslov index, or we neglect it. So included is the black dashed line, if we neglected the gray dashed line. And when we now compare it to the numerical solution of the TDSE in 3D, we see that the black dashed line again matches much better the line of minima, for example, here, than the gray dashed line. So we also see for this non-trivial geometry the influence of Gui's phase anomaly on photoelectron momentum distribution. And to go one step further in our most previous work, I would say, we do not only consider strong field ionization, but we considered the interplay of electron wave packets driven by terahertz pulses and the Coulomb field. And even in such strange looking situation, one can find rescattering phenomena which are quite similar to holography or Coulomb focusing, but under really scaled conditions. And yeah, because we used here a two pulse scheme consisting of a short IR pulse and then a terahertz pulse, by controlling their delay, we could really control the dynamics and also the scattering dynamics to see, for example, for the given delay here, quite nicely also some focusing effects, like in usual strong field ionization, but as I said, under really scaled conditions. And with this, I'd like to conclude. So what we saw is there is Coulomb focusing in electron waves and strong field approximation. I mean, this is not really news. And also already earlier, it was known that the amplitude, so the emission strength of the electrons is modulated by Coulomb focusing. But what we found is that also the phase jumps at this focal point, and hence the interference patterns are modulated by Coulomb focusing. And in order to model it, we developed, or we further developed other semi-classical models and included this prefactor consisting of the Jacobian and the Maslov index. And here the correct weighting with 1 over the square root of the Jacobian is important for the correct signal strength, and the inclusion of the Maslov index, and hence the inclusion of Gui's phase anomaly, is important to reproduce the correct fringe positions in 3D due to the Coulomb focusing. And the implementation of our model was only possible because we were able to solve the inversion problem, which means we were able to determine all initial conditions that were mapped by the classical dynamics to a given final momentum. And to this end, here we used machine learning and we used clustering algorithms. So thank you for the attention.
Thank you so much for your talk. Are there questions, comments? Please put them in the Q&A tab. While we are waiting for the public to ask stuff, there is something I would like to ask you. My postdoc, Brett Augstein, unfortunately cannot be here today, but he sent us a few questions, and I cannot put in the Q&A, so because I'm the chair, so I'll put them in the chat. And he was interested in knowing how you use exactly clustering to solve the inversion problem, and why this preference for the DB-scan rather than other clustering algorithms. I mean, you could have used other ones, and he asked why these specifically.
So we tried, I would say, 3 or 5, which were quite advertised in this Python community. So I think there, if you look at the sci-fi package in Python, and the scikit-learn package in Python, then there are many different clustering algorithms implemented, but you want to have a clustering algorithm which is relatively stable, for example, if you have a cluster which only consists of a few points. And hence a clustering algorithm with noise was, or this DB scan algorithm, which includes here some, or where noise can be treated, was quite good, because then single points which were somewhere in space did not disturb the search of clusters. So usually you have, when you shoot your trajectories, you have some really strange trajectories, which, for example, circle around the core a few times. And this could disturb then the search of clusters, or we saw that it will disturb the search of clusters. So by using such a application with noise, we could avoid the influence. So this is why we have chosen something with noise, and then this density-based spatial clustering, I would say, because it worked. So we tried a few, and this one worked for us best.
Mm-hmm. And the key issue for you was noise, because it was a problem that was very noisy. And
it's not, I mean, noise is, it's not noise what we have. I mean, these are additional physical trajectories, but okay. I would say that they are single trajectories. So as you can see here, a cluster is formed probably out of 5 points or at least 10 points or something. Mm-hmm. But you can have some additional trajectories which also lead to the given final momentum, but they are probably quite strange. And this is important if you especially go to small initial momenta. Then the trajectories which start with small initial momenta, for example, can circle around the core a few times. Mm-hmm. I mean, they do not have really a huge weight in the end in the final electron momentum distribution, but they will disturb your search of clusters. And in order to avoid such, I would probably call them chaotic trajectories, we looked for a clustering algorithm which exactly can avoid single points, and the clustering algorithm which can avoid single points is this DB scan algorithm, because there it treats the single points, even though it's not noise in the usual sense, like noise.
Okay. Yeah, they are there, and they're not a huge amount, but they do disturb. I see your point. And I think this comes then to his next question. What trajectory parameters, like initial and final longitudinal perpendicular momentum and times, do you feed to the model, and why? Because I understand you do like a sweeping at the beginning, you launch a lot of parameters, then you propagate, and then from the bin, you propagate back and solve using the clustering. Is this correct?
Yes, more or less. So yeah, we in the beginning sample many different initial conditions, and in principle you can use whatever you want. So it gets more efficient or it gets less efficient. But as long as you sample all initial conditions, when you take in enough points, it should work. But of course, the number of points you need to solve or to sample them properly is different. So what worked for us pretty well is, for example, sampling according to the ADK rate. This at least gives a good estimate. If you want to make it a little better, I would suggest not sampling according to ADK rate, but adding to the ADK rate for example, Gaussian distribution with small lateral momenta, because the small lateral momenta in the end leads to scattered trajectories. So for large angle scattering, you need to start your trajectories with small lateral momenta. And in order, for example, to get a good resolution in the high energy plateau region, as you could see here, we could also nicely simulate this high energy plateau region. There you need large angle scattered trajectories. So in order to make this clustering method quite efficient, we started some additional trajectories with small lateral momenta. But in the end, how you sample these initial conditions should not influence your final result. So it should be independent. It can only, or what depends on this initial choice is how much time you need and how much computational resources you will need. Because the number of points you need to sample depends on the choice of the initial.
Yeah, this comes to the next question, which is, what was the improvement that you obtained by using clustering? Because I know that with direct methods, people need 10 to the 8, 10 to the 9 trajectories to get converged results. So now, how much can you reduce the number of trajectories by using clustering?
Actually, I did not try to scale it to the minimal amount of trajectories, to be honest. I think these pictures I showed here were calculated with 10 to the 8 trajectories. Mm-hmm. I would say the biggest advantage of the clustering algorithm is that it is versatile. So, for example, I would say to find the correct initial conditions for this example of the bicircular field would be quite difficult. And with clustering, we did not need to change anything. So we simply inserted the new shape of the electric field in the Newton equation, and then we started again. And in the end, a new picture came out with a new momentum distribution without changing much. And this is, I would say, the biggest advantage, that you don't have to plug in physical intuition. Or you can at first avoid it. So of course, as I said before, if you have physical intuition, for example, which initial conditions are important for rescattering and so on, you can make it more efficient, but you don't need it.
I see. Yeah, you have quite a few acoustics as well. I can see also in the bicircular field. So how do you deal with bifurcations and also with these acoustics? My question is not from Brad.
Yeah, this is probably the most difficult point. I mean, acoustics are there in semi-classical approximation. So it's not related to the clustering algorithm. It's related to the approximation of the path integral. And in principle, you cannot do nothing against it. So they will be there. Okay, you can go beyond this usual approximation and then use a uniform approximation and so on. But this is, I would say, quite difficult for most problems. Hence, we did nothing basically with it. They were there, and this was okay. Of course, you get a problem if you have an initial condition which leads directly, or which is really close to the caustic, because then your spectral weight blows up in the semi-classical simulation. But yeah, then you get a bright point simply. So in order to avoid it, you could probably not use the Jacobian.
Yeah, but then you lose the stability factor, and you lose the proper weighting, because our method has a Jacobian. We don't have the Maslov indices. We put them by hand, okay, in the linearly polarized field in some cases. But if you remove this, you will get the wrong weighting.
No, I don't mean remove it, but if you don't want to have a hugely blown up spectrum, you could, for example, not use J, but you could use J plus a small epsilon. Mm-hmm. And then you have at least cured it a little. But this is, of course, not treated properly.
Okay. So for those who are watching on YouTube, and there were quite a few of you today, take good care of yourselves. Have a great Christmas, New Year, holidays, relax, and we will be back in late January. So take good care of yourselves. If you would like to ask questions, but you're a bit shy, just hang in there, because you have the chance. And see you soon. Thank you for joining and supporting our early career researchers.